In today's video, we're going to be installing whole home energy monitoring. This will let me monitor my consumption from the grid, the amount of power coming from my solar PV system, as well as more granular monitoring of a few different circuits to let me keep track of where power is being used. My plan is then to get all the data feeding into Home Assistant so that I can monitor it, analyse it, and even potentially set up some automations based on my power consumption. And we'll be doing this with the Refoss EM06P, which they've very generously sent me over to take a look at. And just so that I'm completely upfront, Refoss did send me this free of charge to take a look at, however no money changed hands, they haven't told me anything to say, and they won't be seeing this video before it goes live. But just to be completely transparent, I'll enable the includes paid promotions thing on this video. When it comes to energy monitoring systems like this, there's a bunch of different products on the market. However, most of them are purely cloud-based things designed for use with their own app, rather than designed for any sort of completely local Home Assistant setup like I have. And the Refoss EM06, which has been out for quite some time, was one of these. You'd use their app to set it up, link it to a cloud account, and it'll work. And since then, they've introduced Home Assistant support, but setting the device up still requires use of their app and a user account. However, recently, they launched this enhanced model, the EM06P, or as the box says, the EM06 Pro, I'm guessing the P stands for Pro, and this is essentially the same thing as the regular EM06, except this supports fully local control. You can set it up without any sort of app, access it through a local web interface or JSON API, and integrate it with Home Assistant directly over the local network. So that'll make it great for my setup, and it's always great to see more and more companies starting to release devices like this, rather than sticking to purely cloud-based solutions. Of course, you can set this up to use their app and cloud connection, all that sort of stuff if you wanted to, but in this video I'll be focusing on the local setup with the Home Assistant side of things, because that's what I'll be using it for. So now, let's take a look at the kit. In the box, we get the energy monitor itself, then under here we get a cable that we use to connect it to the mains, we'll take a look at that shortly, and then we get 6 of these current transformers, or CTs. That means that with this system I can monitor up to 6 different circuits, which will be really useful to keep track of where I'm using electricity. Each of these CTs is rated up to 120 amps, as you can see on the box, and they're what is known as split core, which means you can open them up using this clip here and clip them around the wire without needing to disconnect anything. Then each CT has a nice long cable attached, really long, and then has connectors on the end, these little plugs, that'll plug into the energy monitor itself. So this does mean that it's very easy to install, but it does somewhat mean that you're limited to the CTs that they include, rather than being able to install your own CTs if you prefer. Some other options, sort of products in this market, provide screw terminals rather than these plugs, which means you can kind of swap the CTs out if you wanted to. Realistically, it's not a huge issue though, since these CTs seem to work pretty well, and even though they're rated up to 120 amps, they seem to be completely fine measuring much smaller currents. The only downside is that they are very large compared to much lower rated CTs, so they might be a bit of a squeeze to install into some consumer units. That said though, what's really good here is that if you look at the cable and try and find it somewhere on the cable, we have the rating on it there. And you might be able to just about make out there that this cable is insulated to 300 volts. And this is important, since based on the UK's wiring regulations, if you're mixing band 1 and band 2, or mains voltage and lower voltage cables in the same enclosure, they should all be insulated to the highest voltage present. That means that since these CT cables are going to be installed in a consumer unit with mains voltages present, the cables need to be insulated to handle that mains voltage, which these are. Whereas some other CTs may come with wire that just isn't rated to such high voltage, so installing those in a consumer unit in the UK technically wouldn't be compliant. Now the final thing that's worth bearing in mind with these CTs is what I suspect these are what are known as unburdened current output CTs. The way these work is that, well, they're a transformer. You pass a current through a wire that's passed through the core here, and then the CT will present a current that's sort of proportional but smaller to the current passing through it on its output. The other type you can get are voltage output CTs, where they produce a voltage on their output that's proportional to the current that's passing through it. Now, the important thing to bear in mind with unburdened current output CTs, which is what I suspect these to be, is that you should not connect these to a wire with current passing through it unless you've either connected this end to the energy monitor or you've at least shorted the outputs of the CT together. If you pass current through these with them just sitting disconnected, you can end up generating a very high voltage on the output connector, which is not only unsafe, but you also risk damaging the CT. So the solution to this is very simple: connect the CTs to the circuit you want to monitor with the power off, then plug them into the energy monitor, and only then turn the power back on. Just something to bear in mind. Then next up, we have this cable that's used to connect the energy monitor to the electricity supply. Now, you may be wondering why this needs a mains connection rather than just some sort of DC power supply, and that's so that it can monitor the mains voltage to allow it to calculate the power value. If you see an energy monitor like this and all it takes is a DC input, then all you'll be able to do with it is measure the current, not the power, since you don't have any sort of voltage reference. This cable connects the energy monitor with this 4-pin connector here, and then we have four different wires that come out. We have, you can see the labelling, we have neutral, we have LA, LB, and LC on these wires here. And that's because this device can work with systems with anywhere between 1 and 3 phases. So on a 3-phase system, you connect each of these live wires to each of your phases. On a single-phase system like I have here, you'll just connect all these up to the same line or live conductor, so they'll all just essentially measure the same phase. And then there's also some stuff in the manual about systems with 2 phases, which I presume is more referring to the split phase arrangements you get in North America, where what it says to do is connect one of these to one of your phases, and then connect the remaining 2 to the other phase together. But since I'm in the UK, where almost all houses just have single-phase power, that's what I'll be focusing on for the remainder of this video. And now finally, that brings us on to the energy monitor itself. As you can see, it's a neat little unit that's designed to mount on a DIN rail. So what that means is very much what they advertise you to do with this is you install this inside your consumer unit or distribution board and connect it up to all the CTs. However, I'm not going to do that. Here in the UK, our regulations are pretty strict when it comes to installing things in a consumer unit, and it generally comes down to what's known as type testing. The idea is that the manufacturer of the consumer unit will have tested it with all of their own devices, MCBs, RCDs, RCBOs, and all that sort of stuff. And a large part of that testing relates to how those devices all sort of contribute to and withstand the temperatures inside the board. Especially things like MCBs, circuit breakers, that kind of stuff, they're thermal devices. They heat up, and then when they heat up too much, that's when they trip. So the temperature that they output into the board and the temperatures in the board around them can very much adjust the sort of tripping characteristics and things like that. So what that essentially means is that you're not meant to really mix combinations of devices into a consumer unit that the manufacturer hasn't tested. Or more specifically, you can do it, but you're essentially then taking on all the responsibility from the board onto yourself instead of the manufacturer. You can also maybe see here that it's also a fair bit wider than a standard DIN rail mounted circuit breaker, but not as wide as 2 of them. So that would make it a bit awkward to install into an existing board, since you'd waste an extra space next to this, and you'd probably also then struggle to fit the blank modules around it, which could leave gaps in the front of the board. I don't think things are quite as strict as this in the rest of Europe, where it seems a lot more common to mix different brands inside a distribution board, but just to be on the safe side, especially since this being an electronic device will introduce additional heat into the board, I'm going to install it in a separate enclosure next to my consumer unit, and we'll take a look at that later in the video. Taking a closer look at the energy monitor, we have the DIN rail mount, which includes a little clip here. On the front we have an antenna which hinges up and down, but doesn't rotate left and right. Don't try that because you'll snap it off, and I thankfully didn't break mine when I tried it. And then behind that we have a status LED and a little push button that lets you kind of control state, reset it, and all that sort of stuff. And then on the top and bottom edges we have the connectors. So on the bottom here we have the 4-pin connector that connects that power harness, and then we have a set of 2-pin connections for each CT on the bottom and on the top. Now you'll notice here that these CT connections have designations on them, so A1, A2, B1, B2 and so on. Those letters refer to the phase connections that they're referenced to. And as you can see on the power cable looked at earlier, we have LA, LB and LC. So the letters after L refer to the letter on the CT connection. So what this means is that the CT you're connecting to the A inputs would need to be monitoring circuits on the same phase as the one that you've connected LA to on the wiring harness. Now for me on a single phase setup, that's no big deal, since all these will be on the same phase, so I can just connect on my CTs without much worrying. But if you're monitoring a setup with multiple phases, you need to bear this in mind. You couldn't connect this to, say, a 3-phase supply and then decide you want to monitor 3 circuits on L1, 3 circuits on L2, and not monitor any circuits on L3. Your CT inputs are fixed to 2 CTs per phase. So now, before we install this properly, let's quickly test it out on the bench here. So first of all, we need to power this up, so I'm going to use this Clift quick test, which just allows you to make very quick connections to the mains. So now that connected up, we have the neutral wire connected to the neutral terminal, and all 3 line wires are connected to the line terminal. And we have the other end of that cable plugged into the energy monitor. So now let's turn it on, like that. LED should come on. I'll just wait for it to start up and connect to it. So now with all that connected up, that's now broadcasting an unsecured Wi-Fi network that I've connected to from the PC here. So with that connection made, we can now go to 10.10.10.1 in a web browser, open up that there, and it opens up the web interface for the device. So that's been now connected here. Of course, if you didn't want to do that, you can use the app. The app will then use Bluetooth to find it and set it up that way, but you do need a user account to use the app. So here we are all set up completely locally without the app. So we're connected to the local access point. What we can now do is go into the Wi-Fi settings here, and in here we can set this up to connect to my Wi-Fi network. It's also quite nice here that it seems to be an option to connect to two different Wi-Fi networks, potentially for redundancy, not quite sure. But all we'll do in here, we'll go in here, pick my network, untick open network so I can enter a password, save settings, and that'll connect me to the Wi-Fi. And there we go, that's now connected to my Wi-Fi network, and as you can see here, it's giving me the IP address that it has. So what I can now do is disconnect from this device's access point, connect back to my normal network, go to this IP address, and the web interface should come back up again. So now I've disconnected from that access point, reconnect the computer to my main network, and now I can go to that IP address, and up comes the energy monitor. So now the energy monitor is completely on my local network. There's a couple more things you might want to do, because right now that's still broadcasting that unsecured SSID, so we go into settings, access point, and if we just untick that, that turns that off so it stops it broadcasting its own Wi-Fi network. Now it's only connected to my network, not broadcasting its own. And we also can come into here and go to cloud. If we don't want to use the cloud, which is enabled by default, we can turn that off. So now it's completely not cloud connected, and then we just need to reboot to make that change apply. And now with all that connected, here we can see the web page showing the current readings. And as you can see, I was able to set this up completely locally without any sort of app or user account, which is great to see. The only thing to bear in mind is that this only applies to the EM06P. The older EM06 does still require an app and user account set up, so just double check what one you're buying. Now, the only thing you might notice that's a bit weird or different here is when we connect to the Wi-Fi, we got one IP address, and you'll now notice I'm connected to an IP address on a different subnet. And that's because I found something a little bit weird. When I connected in the sort of last clip, I connected to my IoT network that doesn't allow outbound internet access because this device is completely local, it shouldn't need that. But when I connected to that and loaded up the web interface, it loaded, but I wasn't getting any readings. The voltage was 0, I connected to a CT, it wouldn't read that. There was absolutely nothing being read, which is very strange. So I've now reconnected it to my IoT network that does allow outbound internet access, and it's working fine. So I'll need to go in and do some packet capture and see what it's doing. I don't think it's using some sort of internet service to do any of this, because if you block its internet access once it's started up, it works fine. I suspect there's maybe just some sort of firmware bug there that if it can't make an initial connection to maybe check for updates or something like that, it then fails to load other things and doesn't work. So just bear that in mind. You, at least with the current firmware version, you do need to allow it to talk out to the internet, even if you're not using the cloud. Otherwise, you don't get any readings here. And that confused me, and I thought I'd broken it because I'd previously tested it on my normal network. So when I set it up and wasn't getting any readings, I did think I'd broken it or something. But yep, now it's on a network that does allow outbound internet access. We are now getting readings. And now here in the web interface, we can see the energy readings for each of our 6 channels. Now, of course, we don't have any of the CTs connected, so we aren't seeing any current readings, but we can see that we're already reading a voltage for each channel. The voltage is slightly different between the channels, but I suspect this is just because it's sampling each of them at slightly different times. Then inside each channel, we can see the information that it collects. We get the voltage and current as you'd expect, but we can also see that we're also collecting the power and the power factor. And this is very important. Now, I'm not going to go into the in-depth complexities of AC power here, and I'm probably going to end up heavily simplifying this, but when you first learn any sort of basic electronics, you're taught P equals IV, or power measured in watts equals voltage times current. And with DC, or a purely resistive AC load like a heating element, this is true. But when it comes to AC, things get a bit trickier. Multiplying the voltage by the current doesn't give you the power in watts, known as the real power. Instead, it gives you a value of what is known as apparent power measured in volt-amperes, or VA. The apparent power is made up of 2 different components. The so-called real power measured in watts, which is the power that's actually doing useful work, and what's known as reactive power. Reactive power is a bit hard to explain without going to ridiculous complexity, but essentially it's power that rather than it doing any useful work, it's just moving back and forth between things like the grid and things like capacitors and motors. If you multiply the current by the voltage, you're getting the apparent power in volt-amperes, which is a combination of the real power in watts and the apparent power in volt-amperes reactive, or VAR. And then this number we see here, called the power factor, is essentially the ratio between the real power and apparent power. For the sake of simplicity, if we had a voltage of 230 volts and a current of 2 amps, if we multiply those together, we get an apparent power of 460 VA. If the power factor was 1, then that means that there is no reactive power, so the real power component would be 460 watts. On the other hand, if we had a power factor of 0.9, then that would break down to a real power of around 414 watts and a reactive power of around 200 VAR. And the reason that this is important is that at least in the UK, on a domestic energy tariff, we are billed for real power usage in watts, not apparent power. This does vary between countries, and even in the UK some commercial energy tariffs will bill for reactive power in addition to real power, But if you want to keep track of the power you're actually being billed for, it's important to have an energy monitor that can monitor the real power and not just the current. And it's also important to make sure that the device you're using is definitely calculating the real power properly and not just multiplying the voltage by the current and calling it watts. To measure the real power properly, a device has to sample the current and voltage waveforms very quickly and measure how far apart they've shifted. When I was researching this project, I came across quite a lot of energy monitors that looked great on paper, but when I dug into the hardware a bit more, they simply didn't have the capability to do that. But with this device here, we can see that it's measuring the power factor and the real power, so we're good to go. And then in terms of examples of power factor, I didn't really go into that previously. Something that would have a power factor of 1, so has no reactive power, would be something that's fully resistive, so like a heating element, an incandescent light bulb, something like that. When we're talking about devices that have a lower power factor, that have some reactive component, we're talking about things that have either big capacitors in them, things like motors, things like switch mode power supplies, stuff like that. So generally a lot of stuff you'll have in a modern home, LED light bulbs, that kind of stuff, compressors and refrigeration, microwave ovens, those kind of things will often have a power factor of less than 1, which means that the voltage times the current is not the same as the power in watts. So now, let's take a look at measuring something. So for my test setup here, I have this slightly scary looking extension lead where I've stripped back some of the cable to expose the inner wires. Now obviously this isn't the safest thing in the world, having basic insulation exposed like this, so don't try this at home. This is purely for use as a test setup, don't do this for anything permanent. And obviously inspect this carefully before and after any use. If insulation got nicked on any of these wires and you touched it, you could have a bad time. So now with this setup, we can plug a load into the socket here, and we can connect a CT around the wires to measure the current. And there's a few things to note here, and I'll demonstrate them with this clamp meter just since it's easier to show on camera, but the CTs work in the exact same way. So we've now got a load connected here and powered on, so now let's try measuring this. So the first thing you need to bear in mind is you need to clip the CT around just the line conductor, not the line and the neutral, and not the entire cable. So if we take the clamp meter here and we turn it on and we clamp it just around the line conductor, so just around that wire there, we can see that we're measuring the current. But if instead of doing that we take that off and we clip it around the entire cable, we get 0. And that's because the current's now flowing in both directions through the clamp meter and the currents are cancelling each other out. And this would work in the exact same with a CT. Similarly, if we connect the meter around both the line and neutral wires together, like that, change the range on that, we can see we are almost getting 0. There's maybe a very small current flow here, and that represents the earth leakage. Now, that's another use for this sort of scary extension lead. It's quite useful for sort of measuring the earth leakage of an appliance using a clamp meter like this, if you want to sort of diagnose, say, things like RCDs tripping, but it's not sort of any value that's going to be useful for measuring your power consumption. However, you don't have to connect the CT around the line conductor. As you can see here, we're getting a reading on the line conductor of, what, 360 milliamps or so. But if we come off of that wire there, and instead go around just the neutral on its own, as you can see, we're measuring the same value. And that's because, excluding any earth leakage, the same amount of current will flow up the line and then back down the neutral. And this is just something that's very handy to keep in mind, since when you're installing the CTs, you may come across situations where it's easier to install it around the neutral wire instead of the line wire. There might just be a bit more slack on the neutral, or your neutral wire may be connecting to sort of terminal bar somewhere in your consumer unit where there's a bit more space around it. And for my setup here, there's definitely a couple of circuits that I'm probably going to do that with, so stay tuned to see that later in the video. And the final thing to note is that when you're installing these CTs, is you have to install them in the direction of the current flow. On these ones here, it's labelled with these letters K and L with an arrow in between them. You should normally install these so that the arrow points in the direction of current flow. So this arrow should point away from the power supply and towards the load. So for this sort of test setup here, you'd want the arrow pointing away from the socket and towards the device we're wanting to measure if we're putting it on the line conductor. If you install this the wrong way round, what will happen is the energy meter will read negative values for the power and the power factor, and with this particular meter, it will track those negative values as production or generation instead of consumption. So what that means is if, like me, you have some sort of solar generation or battery storage, if you have the CT around your grid connection and you're importing from the grid, you'll get a positive value for power, and that will be tracked as consumption, and then if you start exporting power to the grid, your power value will turn negative and it will track that as production. The only time this might be a bit different is where I want to put a CT on the circuit that's connected to my solar inverter. If I install the CT with the arrow pointing in the direction of current flow, which would be away from the inverter and towards the rest of the circuits, the readings will be tracked as consumption rather than production. So with that, it may be preferable to treat it like any other circuit and point the arrow towards the inverter. So that any generated power gets tracked as production, and power consumed by the inverter when it's not generating, or potentially charging batteries if you have battery storage, will get tracked as consumption. So now, let's test it all out. So I've clipped the CT around the wire here with the arrow pointing in the direction of current flow towards the socket, and then I've connected the CT into the energy monitor and powered it all up. So now with all that set up, we can see the readings from that port on the screen here, and if we turn on the load, for which I'm just using a hairdryer to test this out, turn on that hairdryer, we'll get a reading. Takes a little second to refresh, but there's a reading, but it's negative. Yeah, there's something weird that seems to be going on here. So yeah, this is something weird where I found that either my CTs are wired the wrong way round, or they're labelled the wrong way round, because as you can see here, it's pointing in the right direction, in the direction of the current flow, but I'm reading negative values. I checked out a couple of other reviews people have made, and I came across a couple where people have mentioned that they had the same thing. So I suspect it was maybe just a bad batch of mislabeled CTs going around, and that's what I have here. Now, it's not a big problem by any means, all you need to do is swap it the other way round, but it's just something to bear in mind. What I'm going to do now is I'm going to check each of my CTs on this test setup and relabel them so that I know the arrow is pointing in the correct direction. I'd also recommend that you do the same just in case. That said, if I hadn't realised this in advance and I'd already installed all the CTs, it's not the end of the world. If we come into the web interface here and then go to Settings and Circuit Factor, we get this page here. And these values are essentially multipliers that let you adjust the power readings from each channel. By default, they're all set to 1, but if you had a CT installed the wrong way round, all you need to do is change that channel to -1 and that'll flip the values around. You can also set this to different values here to slightly tweak the numbers to calibrate it, or what it says up here to enter 2 to monitor the current consumption of a 2-pole breaker. This wording doesn't really make much sense to me, but what I suspect this is talking about is in the US with a split phase supply, this device will be measuring the voltage between each phase and neutral, which would be 120 volts. Whereas if you had a 240 volt device that's connected across the phases and a CT around one of those wires, you'd set this to 2, which would double the measured power to compensate for only measuring half of the voltage. I think. Don't quote me on that. So there we go, I've now relabeled all my CTs, so I'll be using them this way around for the remainder of the video. Of course, this may be different to your CTs might be labelled correctly from the factory. I would just recommend testing them before you go and install them into a sort of live environment. And there we go, so that's the CT now installed the correct way around on the cable, so that's on there. And if we turn on the load, wait for a second for it to refresh, we can see we're now getting a positive value for power and a positive power factor. Similarly, if we wanted to, we can move the CT onto the neutral. So we can take it off the line there and put it on the neutral. And because the current's flowing in the opposite way down the neutral, we need to install the CT in the opposite direction. So we install that around the neutral that way. And as we can see, we now have it so that the current flow is pointing away from the device and back to the source. And then once again, with this setup here, if we turn on the load, look up at the screen, refresh the page, we can see we're getting a positive value for power, and this time we're measuring it on the neutral. It's also worth mentioning, although I don't have a second breakout adapter to demonstrate this, that you can pass multiple wires through the same CT, and you'll essentially just measure the total current flowing through them all. You just need to make sure that the current is flowing in the same direction through all of them, otherwise you'll end up with the currents cancelling each other out, and you need to make sure that you don't go beyond the maximum rating of the CT, in this case 120 amps. But that can be a good way to monitor multiple circuits, the total power consumption of multiple circuits, with a single CT. So now, let's do a couple of tests to see if we can measure the accuracy of this. So for this test setup here, we have the current monitoring system all set up, monitoring this socket here, and I've also plugged this into this plug-in power monitor that I generally trust the accuracy of. I've used this a fair bit, and it seems to be pretty accurate. So we can measure the power consumption both through the CT in the interface here, and on the plug-in power monitor, and compare the values. I don't know if the screen on this thing's showing up particularly well, so I'll read the values out in case it doesn't show up on camera, but should be good to go. So first test we're going to do is with a purely resistive load, which is this toaster. So this is a heating element, it's not got anything in it, no motors, nothing like that, so it should be purely resistive, meaning that the current times the voltage will be the amount of power in watts, and it should have a power factor of 1. So now, let's test this out. So if we turn the toaster on, we can then refresh this page here. We're getting a reading of around about 1134 watts. Down here we're getting 1133 watts, so yeah, pretty close. Of course it'll jump around a little bit, we're reading them at sort of instantaneous times on 2 separate devices, so we'll be reading them at slightly different points in time. But then 4.74 amps or so. Down here we're reading 4.79 amps, again that's different times again, so yep, all seems pretty accurate. And obviously with this being a purely resistive load, we have a power factor of 1, meaning that if we multiply the voltage by the current, we will get the exact same value as we have in watts. So now what I want to do is test with something that's got a much worse power factor. So I dug around trying to find a device that's got a really low power factor. Turns out that actually most modern stuff's pretty decent. Tried all sorts of power tools with big motors. They were all kind of power factor like 0.95 sort of thing. But then I found my old firewall, which does have a pretty poor power factor of 0.5 to 0.6. So pretty poor power factor. So if we plug this in, we can take a look at what we get for measurements. So plug that into the power there. Take a little second to start up, and the power will change around while it's starting up. And let's take a look at the readings. So now first up, take a look at the plug-in meter here. We can see we're drawing around about 20 watts from the wall. If we check the voltage, we're at 237 volts. And if we look at the current, we're looking at 0.163 amps, so 163 milliamps. So if we do the maths and multiply that voltage by that current, we get a value of 38 VA, so 38 volt amperes. So as you can see, that's significantly more than the 20 odd watts that we're drawing from the wall. And as you can see, if we go to the next screen on this to get the power factor, we can see we're getting a power factor of 0.55, 0.56, which explains why we're getting that, because this has a very poor power factor. But now, if you look at the Refoss interface, I'm getting some quite strange behaviour here. As you can see, right now, it's measuring a power factor of 1 and 37 watts, which is not right. This thing has a power factor of about 0.5 to 0.6. But then if we refresh the page, it kind of eventually will kind of change. So now we're getting 0.78 power factor, still a bit too high, but at least something. And then now we're getting 0.6 with 20 watts, which is about correct. So the power factor readings for my setup here seem to be a bit weird. What seems to almost be the case here is that the minimum power factor that it sort of reports at this point, there 0.58, that's correct at that point. The minimum power factor we're getting showing up here is correct. It never seems to underreport the power factor, but it seems to sort of quite often spike up to 1 or very close to 1 periodically, which is throwing all the values off. So as you can see there, it was reading the correct power factor, and now it's jumped back up to 1 again. So there's something really weird going on here with how it's kind of measuring the power factor, and it's not keeping a consistent value. And I've tested this with a bunch of different devices, a bunch of different sensors into different ports on the CT, all that sort of stuff. And it all seems to have basically the same behaviour, where the minimum power factor value recorded is generally the correct one, but it only seems to record that value periodically, and then in between those times it records a much higher power factor that doesn't really make sense. And of course the issue with this is you're going to end up, if it keeps doing this when it's live, you're going to end up over-reporting your power. You're going to get power values that are too high because it's assuming your power factor is higher than it is. As you can see there, we're now at sort of the correct power factor and correct power level again. It's weird. Now, I'm not going to pass too much judgment on it right now, just because right now I'm on the desk here, I've only got one CT connected, I'm drawing a relatively low load through it. There could be something weird going on just with my test setup. So what I'm going to do is I'm going to get it installed anyway, we'll measure it all out and see what happens when it's live, and then we'll talk about it. What I can also do when it's live is I can then record things like my daily power consumption through this, which will come in through in kilowatt hours. I also have the reporting from my smart meter, which includes daily or even half-hourly reporting, so I can compare the values from my smart meter that I definitely trust to be accurate and this to see if this actually affects the overall recorded values, or it's just a weird sort of glitch with how it's instantaneously displaying it here. Hopefully if it is a bug, it's something that can be fixed through a software update, or what I could potentially do, and I'll maybe try later in the video, is once I've got this data pulled into Home Assistant, I can maybe do some sort of maths on it to help figure it out. You know, collect the voltage and current every time it updates, collect the power factor every time it updates, but then calculate the power using kind of like a rolling window of the last 5 or 10 power factor readings and take the minimum value that was recorded in that window. Something like that. I can play about with it. But at least if I get this installed, I can then start doing the maths, get the data collected, start doing the maths, figure out how to calculate the correct values if it is causing a problem in the collected data, and then we'll see how we get on. But yeah, a little bit weird there. Hopefully it's something that can be fixed through a software update, or it's just a weird glitch with my test setup here, but the only way to figure that out is to get it installed. So now it's time to install this. So as I mentioned earlier, I'm not going to install this inside my consumer unit, I'm going to install it in an enclosure next to it, and then I'll run the CT cables into the consumer unit. So we have the energy monitor here, and for an enclosure, I've got this little enclosure here. This is a cheap little Axiom branded 2-module DIN rail enclosure. It's a cheap thing from Toolstation. But the idea is it holds 2 modules, and it's quite tall, because you get a lot of these that are quite short, but when you factor in the cables coming in and out and the strain relief on them, you do need something reasonably tall. Then in terms of powering it, obviously I have the cable here. Technically, you could just wire this straight into a plug. The problem with that is that this enclosure here is metal, so it should really be earthed. So what I'm going to do, instead of just wiring these directly in, I'll wire a mains flex into this, where I can then connect the earth into the metal casing here, and I'll put some terminal blocks in where I'll connect this cable here up to that flex to connect the 3 lives to the live and the neutral to the neutral. And there we go. So it's now all assembled in the enclosure and ready to be installed. So what I've done here is I've taken that enclosure, I've then drilled a hole out the back and then used a bit of earth sleeving as grommet strip just to let me feed the CTs through, because the way my consumer unit is installed, it's installed on a sort of raised board with a big void behind it. So I can feed the cables out the back of the consumer unit through that void and through the back of this assembly. So drill that hole out there. Now we've got that. Probably should have done it higher up so it doesn't catch on all this, but that'll work fine. What I've then done to power it is I've run this piece of flex in through this stuffing gland at the bottom. Using a bit of flex just means I can plug it in. It makes it easier than sort of hard wiring it. I can unplug it, plug it back in again, and it's not classed as like part of the electrical installation. It's now just like a plugged in appliance, which is a bit better to work with. So I'm going to do that there. So that's going to plug in. And then what I've done is that flex then comes in the bottom. The CPC or earth then comes up the side here and then plugs into the, or connects into the earth terminal. So that just earths the whole case. The stuff inside doesn't need it. It just needs to earth the whole case. And then for connecting up the energy monitor, what we've got is the original breakout cable that we had before. I've left loads of slack of that stashed in here. I just don't want to take it all out because, you know, it's a sort of proprietary cable like this. You don't want to kind of cut it really short and then never have that space because it's not a cable you can easily replace. So I've left most of the slack in there. And then what I've done is I've brought those all around it here. And then we've got the cable that comes in, so the line and neutral that come in, go into these 2 Wago terminals. It's a really neat little Wago 221 DIN rail carrier. Got a bunch of these, they're actually really nice. So that mounts on the DIN rail there. I have a pair of Wago 221s, one here for the neutrals, so those 2 neutrals come, so the neutral comes into that and then comes out onto the fly lead, onto the neutral there. And then the line comes in from the flex into here, and then the 3 different lines, A, B and C, go off the energy monitor. So that's now all installed there and ready to go. So let's try and work out how we're going to get this on the wall. It might be a bit fiddly once all the CT cables are in here, but let's go downstairs, take a look at the consumer unit, how we're going to install it, and get it installed. Okay, so now here I am, my understairs cupboard with the consumer unit, so let's take a look at how we're going to install this. So here at my consumer unit, as you can see, it's pretty wide here, but there's just enough space in here to sneak that additional board in. And there's a socket up there so we can plug it in to power it fairly easily. And in the consumer unit, we've also got a bunch of circuits. And they're kind of spaced out in groups that are almost the groups I'm going to be monitoring. And having these spaced out will be really useful because it means that I can get the CTs in because there's spaces between the sort of individual CTs rather than having them all bunched up to one end, loads of blanks over here, and then you'd be really bunching the CTs up and you'd probably struggle to get them all in. So from left to right, we've got solar PV, so that's going to get its own CT to monitor my solar generation. Smoke alarms and central heating, I'm not going to monitor these just because it's such a low sort of draw, it's really not going to be any sort of significance or worth monitoring. When it says central heating, it's a gas boiler, so all that's really powering is sort of the boiler itself, the pumps and the controls. It's not really powering anything significant. Then we have the upstairs lights and downstairs lights, so we're going to power those, put those through a single CT, so we'll have one CT just monitoring lights. We have one for comms rack and alarms, that's my comms rack. I'm going to monitor that on its own, because that's the whole comms rack, audio system, CCTV, anything that's powered over Power over Ethernet is done through this. Then we have 3 separate socket circuits, so upstairs sockets, two upstairs socket circuits and a downstairs socket circuit. I'm going to monitor those on one CT, so I'll have one CT just monitoring general sockets. Then finally here we have kitchen sockets and cooker. I'm going to monitor those together because that's essentially going to be the kitchen all in one, because the kitchen sockets includes things like the fridge, the dishwasher, all that kind of stuff. So that's my sort of individual CTs. So we have 1, 2, 3, 4, 5. Then the final CT is going to be down this end, it's going to go on the grid, so that'll be my grid connection there. That way I can monitor my consumption and export to the grid. I can monitor my solar generation, and I can get individual sort of monitoring stats for my lighting, sockets, kitchen, and the comms rack. So yeah, that should all be good to go. So what we now need to do is get all these CTs installed. So of course now the next step involves taking the front of the consumer unit to install the CTs. Now I'm not going to go into too much detail on this, but basically do not do this unless you're competent and you know what you're doing. This isn't the same as just wiring a plug or changing a socket. Make sure you fully know what you're doing, and if in doubt, get a qualified electrician in to do this. What I'm going to be doing is making sure I safely isolate the consumer unit using proper equipment to do that. Don't just turn it off and hope it's off. Make sure you've got the proper equipment to safely isolate. If you have any doubt in how to do safe isolation, make sure you know how to do it or consult an electrician. For all these sorts of things like safe isolation, all this sort of stuff, I'd strongly recommend checking out the GSH Electrical YouTube channel, who have loads of detail and proper training on how to do this sort of stuff. So we're going to safely isolate the consumer unit, get everything turned off, locked off and isolated, and then we can install those CTs. And there we go, that's everything now fully locked off and isolated, so the board's isolated here, everything's turned off. And I've also locked off the double pole isolator at the incoming supply as well. It's worth doing that, don't risk these things. That double pole isolator is very much at like knee height, and if you lift it up, that turns it on, so the last thing I want is to get caught on something and accidentally turn it on, so locking it off is a lot safer. And yes, you're not really technically adjusting any live wires or actual wires in this job, you're just clipping CTs around it, but don't risk it, you're putting your hands into a board, there's little ends of the bus bar that can be live, there can be bits of copper sticking out of things, a wire could be loose and come out of a terminal. Don't risk it, fully isolate everything. So everything's now fully isolated and locked off, it's now ready to install it. So what I've done here to install the CTs is I've drilled a little hole here for the CT cables to go through. This is where I'm mounting the monitoring board, and there's a complete empty void here so I can get the cables from through here and into the back of the board here and then in here somewhere. In terms of circuits, as we saw before, we've got the solar circuit, that's going to be easy to install. The lighting circuits, we can again pull those two lines forward and put those through one CT. The rest of the circuit is going to be a bit more awkward because I've got these AFDDs which are really tall. Really quite interesting, essentially they're arc fault detection devices, so they do everything a regular RCBO does, so overcurrent protection, residual current detection, or ground fault detection as you call it in America, but they also detect electrical arcing, so like a loose connection, a damaged cable, something like that. So they're a good little device, pretty new, but they're quite cool. But the downside with these is they are very tall. You can see compared to a standard, a miniature RCBO, they're way taller, and compared to even a full-size Hager RCBO, they're still way taller, and they're way deeper as well, front to back, so there's no space behind them, stashed cables behind them, which makes it a little bit awkward and not very neat. So for this one here that feeds the comms rack, I should be able to get a CT on that just because the wire's in there, so I should be able to squeeze it in. But then the sockets ones and the kitchen ones, there is no chance I'm going to get a CT around these without really bending them and sort of contorting things. So instead for these two circuits, CTs, what I'm going to do is use the neutral fly leads, because with these being essentially RCBOs, they have line and neutral into the top, out to the top, live in it, or line or live in at the bottom for the bus bar, but then the neutral is carried in over these fly leads that connect to this neutral bar over here. So these three neutrals here relate to the socket circuits, and these two neutrals here relate to the kitchen. So I put one CT around these three and one CT around these two. That will handle the sockets and the kitchen circuit. And finally we have the grid CT that can just go onto one of these 2 meter tails over here. I'll see how I'm for space here, fitting that CT into the board. If it's just too tight to get it into here with everything else going on, what I can always do is I can always bring it out of the board and put it onto one of the meter tails outside of the board instead, but we'll figure that out. So yep, I'm conscious that my UPS is beeping through there and it's about to run out of power, so time to get a hurry on, get all this installed. So there we go, that's all now installed. And yep, I know the front is off with the power on. I installed it yesterday, so I've just taken the front off just to shoot this bit. So don't try this at home, and I'll be doing all my pointing with an insulated screwdriver because don't want to have an incident. But yep, that's all now installed. So on the left here, we have the energy monitor installed in its enclosure. The CT cables then go through that hole in the wall, and then most of the slack is stashed behind this board here. There's a bit of slack sort of looped around inside here. Then for power, the cable comes out of here and then goes up, and it's plugged into this socket up here for power. And then inside the board, we can see all the CTs. So we have one CT around the line conductor for the solar, one CT around the line conductor for the 3 different lighting cables going out, so that's 2 different lighting circuits, and then one of them has 2 cables in it. This CT is around the line conductor for my comms rack circuit. And then, as I mentioned before, because these circuits are all so close together, there's not much space, and I want to monitor sort of 3 circuits in one CT for the sockets. Rather than putting the CTs over here, I've put them around the neutral conductors. So we have this CT here that goes on the 3 neutral fly leads for the socket circuits, and this CT here is on the 2 neutral fly leads for the kitchen circuits. And that's all installed absolutely fine. Definitely have to say though, these CTs are very big. Compared to other systems where you can kind of buy smaller CTs, you might have, say, a 100 amp CT for your grid connection, and then maybe some sort of 50 amp CTs and 20 amp CTs for your general circuits. Using these 120 amp CTs for everything does mean that they're very big, and trying to get them in here is really awkward. In fact, if these breakers hadn't been spaced out like this, I would have really struggled to get these all in. It is all absolutely fine though, the cables all run neatly round, kind of behind the breakers, behind the DIN rail, come up and out and into there, so it's all absolutely fine, but it is very tight. These are very large CTs. The other thing you'll notice that is kind of lacking from in here is the grid CT. What I ended up doing was, instead of installing it inside the consumer unit here, I brought the cable out the stuffing gland at the bottom and connected it onto the meter tails externally, and I'll just clip this up and out of the way. The reason I did that is just because, as you can see, the meter tails come in here and curve round. there's already a CT kind of in this area, and these meter tails, they're not nice flex tails, they're just standard tails, so they're very, very thick and very stiff. There's not really any flexibility to bend them, so trying to get a CT in this area would have just been a bit awkward. The other thing you need to watch is that these CTs, the core in them is a ferrite core, and it's very brittle, so you do not want to try and force these, clamp them around something where you're squeezing it shut, trying to get it to shut, because the risk is that you'll crack the core and destroy the CT. So with these cables here, because they're bent round, what would end up happening is if I try and clamp a CT onto this, because it's got a curve in it, it would potentially be too tight, I'd crack the core potentially. There was no point unnecessarily trying to shove more stuff in here, so instead bringing that meter CT out and connecting it externally was just so much easier, so that's what I've done there. But yep, that's all now installed. So with all that now installed and powered up, let's get the front back on all this, jump back up to my studio, and get this all integrated into Home Assistant. So there we go, that's all now closed up, and as we can see, we've got the energy monitor in its case. I've put a blank in to cover the sort of excess space next to it, and that's completely neat up there. And as you can see now, with it all installed and up and running, it's working. So now here we have all the different readings for all the different CTs that are installed across all the circuits. As you can see here, I've also renamed each of these, so you can go into Settings, Device Name, and then you can rename these to the sort of the different device that they represent, which makes it a bit easier to understand. That's most of what there is for the web interface. A couple other things to take a look at. The Actions section here lets you create these things called actions. Essentially, it's like little automations, so you can put in a name, set some time ranges, set events such as a particular input. When the consumption, the power, whatever, changes a certain thing, you can then make it call a web URL as like a web trigger. You could use this for things like if you're exporting power to the grid and you don't want to export power to the grid, you could then trigger a URL that would turn on an appliance to use that power rather than exporting it, that sort of thing there. So it does have that sort of automation built in, although I'll be doing all that through Home Assistant. That's basically everything in here. Only other thing is you can enable MQTT here. So if you want to connect to MQTT and publish data to that, you can do that through in here. Then the final thing is obviously right now this web interface has no authentication. If you wanted to lock that down, you go to Settings, Password Verification, and put a password in here. I'm not going to bother doing that right now, but you can set that up if you want. And then we can get into Home Assistant. So to get into Home Assistant was dead simple. We just need to install the Refoss RPC integration from the community add-on store, so from Hacks. There's a couple of different integrations. It's the RPC one you want for this device that has the local API. The other Refoss integration is more for their cloud-based devices. So install Refoss RPC, you then click to add the device, enter its IP address, and that's all you needed to do. It just pulled it straight in. And as we can see now here, we have all the sensors. So it's pulled those names that I set up in the web interface on the Refoss device. They're all pulled through, and we have all these sensors. So for every device I have the current, the power factor, and then the cumulative sums of the month's energy, the month's return energy, the week's energy, and then the day's energy, kind of all cumulatively added. And we also have a voltage for each device as well. So that was dead simple, all pulled into Home Assistant. And then off the back of that, I've been able to add it into other Home Assistant dashboards. So I've got my main dashboard here where I've got one for energy. I've added this power flow card. So this lets me kind of see where the power is coming in from the grid, how much is going out to different things. So some's going to infrastructure, which is the rack, some's going to sockets, some's going to lighting, so on. Of course, there's some things that aren't monitored here. When the solar's running, you can see some power coming from the solar into the house. If it's exporting, it's coming into the house and out to the grid. This works really, really nicely. So this is like instantaneous power, so I can see the instantaneous view of what's happening. And then in addition to that, we can then come over to the energy dashboard, and this is Home Assistant's energy dashboard. So this is more cumulative historical energy usage rather than instantaneous power. So here we have the usage for the day. So we can see we've got my sort of energy usage. The purple is when we're exporting solar. The orange is where we're using solar instead. So you can see, for example, this point here, the blue was all pulled in from the grid, and then this orange area here was power that's consumed from solar. Down here we've got solar production. This is kind of a similar view to the other thing, but this is more for how the energy was used across the whole day rather than it being a sort of instantaneous view. This is for the whole day. Then we come down here, gas consumption. This is separate. My energy provider does report the gas into Home Assistant, but it's like a nightly report rather than being sort of instantaneous. And then because I've got those individual devices as well, I've added those too. So what we have here is this energy flow visualization, which is really cool, where we can see the grid power coming in here, the solar coming in below that. That then feeds into the home, and then we can see from the home, it feeds into the sockets, the infrastructure, and the kitchen energy, and things like that. What I can also do with this is add additional monitoring devices and then set them as kind of having dependencies on these. So for example, I could use a smart plug that monitors power on something that's plugged into a socket, say that it has a dependency on the socket circuit, and what you'd see is the power would come in from the home to the sockets, and then it would branch off again to say, show how much is being used by the smart plugs, and show how much is being used by things that aren't tracked by those. So you can add multiple layers of this and get really detailed flows, which is really cool. Similarly down here, you can see we've got solar. That branches off. Some of the solar goes into the house, and that was the solar that powered the house. And then some of that solar goes to the grid, and that's the solar that was exported back to the grid. And this works really nicely. However, we do have a problem. With my initial demo, I talked about that issue with the power factor fluctuating around. I was hoping when I got it all fully installed, that would kind of stop happening once there was load on all the CTs and things like that. Unfortunately, that's not the case, and I'm getting some really weird behaviour with the power factor measurements. So what we're looking at here right now is the power factor across the entire day for my comms rack circuit. This feeds my rack, which is a very constant load, and I've tested it with a plug-in power meter, and the power factor of that sits pretty consistently around about 0.7. Maybe down to 0.65, maybe up to 0.75, but it's very close to around about 0.7. But as you can see, if you look at these measurements here, it's fluctuating massively. So you can see around about here, it's jumping anywhere from 1 all the way down to kind of 0.7. So the bottom of this kind of line here is about right for the power factor, but we've got these massive spikes coming up, and that means it massively over-reports the power. But it gets even weirder, because this is the power factor just for the comms rack circuit, and now this overlaid on top is the power factor for my socket circuit. So the blue is the comms rack circuit, the orange is the power factor for the socket circuit. And you can see a weird interaction between the two. So both of these are experiencing pretty weird fluctuations the whole time. The socket circuit is tracking a little bit lower than the comms rack, which is probably roughly expected, and kind of overnight when there's not much socket usage, power factor is a little bit lower than the comms rack, and they're both wildly fluctuating, but kind of in the sort of same lanes. Then what happened is round about this time here this morning, I switched on the washing machine onto a wash-dry cycle. Now a washing machine has a very big resistive heating element in it, and that was plugged into the socket circuit. So what would happen is, because it's a resistive heating element, anytime the heating element comes on, that will massively change the power factor of the socket circuit to go much closer to 1, because we've got a big resistive load there. And you can see, if you look at the socket circuit, it does. Heating element kicks on, and the power factor for the socket circuit goes up very close to 1. Then it kind of fluctuates a little bit around here. This is probably when the wash cycle was going on, the heating element wasn't being used as much. Then it switched into the dry cycle, and once again, the power factor for the socket circuit jumped right up. A lot more fluctuations here than before. I suspect maybe when it's in the drying cycle, it turns the element on an awful lot more, or maybe modulates it somehow. But once again, you can see when the heating element's kicked in, the power factor tracks a lot closer to 1, and then drops down again when the machine finished its cycle. Now, that would be kind of expected, and yeah, you've got these fluctuations there, but even with the fluctuations there, that's kind of still what I'd expect. But now look behind this at the comms rack. When the heating element kicked in on the socket circuit, the power factor being measured for the comms rack massively dropped down. Then it jumped up again when the power factor was kind of veering around on the socket circuit again, and as soon as the drying cycle kicked in, again the power factor for the comms rack circuit started fluctuating and dropping down massively. And this is really, really strange. Before I noticed this behaviour, what I tried doing was implementing some smoothing. So I tried it both through some Home Assistant functions and through some Node-RED logic, where I would take the power factor in and I would kind of try and remove the spike. So I try and stick generally towards the lower end of what I'm receiving, because that was roughly what I was finding to be the correct power factor. Remove the spikes, built a little algorithm there, and it generally worked okay and actually got pretty good results. Until this happened. Because what was happening is we had the power factor for the socket circuit, the comms rack circuit, and I was generally tracking towards the bottom of what I was seeing here, and that was fine. Until this happened, at which point the whole power factor being measured for the comms rack circuit dropped way down, and now the correct power factor is actually towards the top here, but instead of tracking that because I had my algorithm, that was tracking towards the bottom here as well, and massively undercounting the amount of power from the comms rack. So previously I was going to say, well, at least with the issue I could smooth it all out, but because of this weird interaction here, I can't, because something like this completely throws off the data, even if it's smoothed. And now here we can see the power consumption in watts, measured with both the power factor straight off the device and after my smoothing of the power factor. The blue is the one straight off the device. As you can see, it's fluctuating around quite a lot. The orange is the one that I smoothed, and that was a much more usable value. You can see around here we're sort of sitting around about 350 to 400 watts, which is round about correct. But then as soon as the tumble dryer and washing machine switched on, that dropped right down, saying that the comms rack was using 100 watts, 200 watts. Funnily enough, turning a tumble dryer on doesn't make your comms rack use less power, so this was definitely not working right. So unfortunately, my smoothing attempts just aren't going to work with this kind of weird behaviour. So I was trying to work out what was causing this, And it turns out that it seems to be to do with those pairs of inputs designed for the 3 different phases. So when we saw the device earlier, we've got the 3 different phase inputs, A, B and C, and on the device there's 2 pairs of inputs for each phase. You've got A1, A2, B1, B2, C1, C2. Now with these 2 circuits here, the comms rack circuit and my socket circuit, those are connected to the same pairs of inputs. So the socket circuit is connected to the B1 input and the comms rack circuit is connected to the B2 input. And that's where this issue seems to lie, is that if you've got 2 CTs on the same lettered input and they have wildly different power factors, the power factors sort of interact weirdly and it throws off the readings in this way. And then just to give a little bit more information here, as you can see what I've now added is this red line, this sort of orangey red line. That is the real power recorded by my PDU. And as you can see, before here, we're kind of tracking a little bit high above it, but not hugely. I'm not too worried about the PDU tracking a bit lower than the energy monitor because PDU isn't counting the UPS's consumption. But then as you can see here, when we dropped down, when that other load came on, it dropped way below that red line. So we were tracking the power as way too low compared to the actual power being recorded by the PDU. And now here's another example, and this is really what showed me where I think the power factor was being caused by different circuits on the same 2 channels were causing the issue. So what we have here is in blue, we have this power factor of my solar circuit, and in orange, we have the power factor of my lighting circuit. And once again, these are both on the same lettered inputs on the device. So I think the solar is on C2 and the lighting circuit is on C1. As you can see here, overnight when the solar is not generating, the power factor on the lighting circuit is actually really, really stable because the lighting circuit's power factor is normally very, very low, close to 0 because there's basically no lights on. And if there is, it'll be like the standby power draw through like an extractor fan's timer or something like that would have a very low power factor. So because these power factors are so similar, there isn't really much fluctuation at all. You can see there's a big spike here where the lighting jumps up much higher. This would have been when I turned on the heated mirror in the bathroom. I've got a mirror that heats up, sort of demist it. I must have turned it on as a night light. The heating element turns on, and it's about a 30-40 watt heating element that's fully resistive, so that will massively increase the power factor. So that would have been that turning on. But as you can see, overnight when the solar's not generating, the lighting power factor is actually really quite stable. But now look what happens as soon as the solar starts generating. The solar jumps down to a power factor of -1, which is what you'd expect. You're exporting power to the grid, so the power factor goes negative, so you get a power factor of -1 the entire day while the solar is generating. And as soon as that happened, the power factor on the lighting circuit started fluctuating much more. There wasn't really any change in us turning on and off lots of lights here, but you can see that as the solar was being generated, the power factor started fluctuating significantly more on the lighting circuit. And then over here towards the right hand side, you can see the power factor for the solar circuit started increasing again. That's when the solar would have stopped being generated. There's a period there where it almost went above 1. That's probably some sort of self-consumption of the inverter. And then it kind of flattened down and went back to very close to 0 again. And once again, once it's very close to 0, the lighting power factor is now higher because there's currently lights on. There wasn't lights on over here. But it's still tracking a lot more stable than it was during the day when the solar was generating. So to me, this definitely does look like the issue is where you've got 2 wildly different power factors on the same lettered pair of inputs. They interact really, really weirdly. The other thing I did just for the sake of argument, just to make sure it definitely wasn't the cause, is rather than having the energy monitor wired into a plug and then plugged into the socket circuit, I tried wiring it directly into a circuit breaker with nothing else on it, so it's on a dedicated circuit. And as you can see, it made no difference. This little gap in the middle here is where I had the power turned off to swap the device over. So left of this and right is where it was wired into the plug, right of this is where it was wired directly into a breaker. There's no difference. They're both fluctuating exactly the same as far as I can tell. So with that, where does this device really stand? Well, right now, unfortunately with this problem, the readings for the power, for the real power and the cumulative power, kilowatt hours, that kind of stuff, just aren't accurate. I can't really use them reliably. Now, if all you want to measure is current, so your current in amps and your voltage, that seems to track completely fine and is completely accurate. Now, I'm hoping this is just some sort of firmware issue that Refoss can fix. If it's fixable and they can get a software update out that fixes this, that'll be amazing, and I'll absolutely leave a pinned comment if this fixes it. And if the fix is even more interesting, I might even do a dedicated video kind of showing that. But right now, it's just not really reliable enough for me to comfortably use and get important stats from. Okay, and now at the 11th hour, as I'm literally editing this video and realising how long the video is, so I need to be quick with this, I've made a discovery that seems to have fixed it. Not properly fixed it, but temporarily made this device usable for me. As we can see here we have my grid power, and as you can see, it's now a lot more stable. We can see that is basically as stable as I'd expect. And then likewise, adding on the power factor as well for the grid, we can see that is so much more stable than we're getting before. There's fluctuations there, that's to be expected, but that's completely fine. It's not like before where it was completely spiking up to 1 and basically making no sense at all. However, the solution for this isn't exactly ideal. As we talked about before, the issue seems to be where you have two different CTs on the same letter of input that are getting wildly different power factors. So what I thought I would do is, instead of that, I'd make it so that each pair of CTs on each lettered input is measuring the exact same power factor by making them all measure the same circuit as each other. So essentially, I've doubled up the CTs onto each of my circuits. So I have two CTs on the grid connection. Those are wired into A1 and A2 on the energy monitor. The two CTs on my socket circuit are wired into B1 and B2. And the two CTs on my solar circuit are wired into C1 and C2. And having done that, the results are now completely stable. In terms of the accuracy, here we have the energy dashboard for the first full day that I had it installed with those CTs doubled up. And as we can see, it's reporting that I imported 15.1 kilowatt hours from the grid and exported 0.85 kilowatt hours. Taking a look at the same day on my energy providers app, it's tracked me as pulling 15.4 kilowatt hours from the grid and exporting 0.9 kilowatt hours. So very, very, very close. We're 0.3 kilowatt hours out on the import, and then the export is essentially a rounding error because their app only shows me at 1 decimal point. So with that setup with the CTs doubled, the accuracy is perfect. I can't see any issue there at all. However, if we go back to the previous day, this was before I moved those CTs. I think I moved them round about midnight, so right towards the end of the day. So this is back when the CTs were on individual circuits and we're measuring just the same power level, but with the CTs separated out, where we're having that error. And with this, it's saying I imported 24.7 kilowatt hours from the grid and exported 1.02. Whereas in actual fact, I imported 19.5 kilowatt hours from the grid, so close to 5 kilowatt hours less than this is reporting, and I only exported 0.5 kilowatt hours compared to the 1 this is reporting. So as you can see, before I did that without the CTs doubled up, I massively overcounted the amount of energy I actually imported and exported from the grid, which isn't right. The final thing I did was taking a look at my kind of usage pattern compared to my energy providers app from that test I did where I tried to smooth the data out, and it was better than what we see here, where my sort of calculation with my smooth data, I estimated 15.7 kilowatt hours from the grid. According to my energy providers app, I drew 16.37, so a lot closer. But the difficulty is with that smoothing being so impacted by the power factor on different circuits, it could wildly change depending on what sorts of loads I'm using, so it's not really accurate. So at least now with this setup, I am now getting decently accurate stats across my grid, solar and socket circuits, but I'm not really able to monitor those other circuits like I really want to be able to do. And then finally back here, we have this kind of live power dashboard. We can see power coming in from the grid, going out to the comms rack. That energy, that power is now coming from the PDU's direct measurement rather than a CT. Sockets are all being monitored there. We've got this other entity here that's kind of going to be everything else. So kitchen, lighting, smoke alarms, boiler, that kind of stuff. These numbers probably still won't exactly add up. There's always going to be little bits of errors in there. And also you need to factor in these will all be being sort of sampled at completely different times to each other. So they might not completely line up, but it's a lot more accurate. So I found a slight solution there. It does mean I can use this system now, but I really hope Refoss can find this bug and fix it. After I put this video out, I'll drop them an email, let them know I found this issue, and I'm happy to work with them to try and find out what this problem is, and if they release any future firmware updates, or even just find a weird thing that I've done wrong or something weird with my setup that's causing this that I can fix it with, I'll happily put a pinned comment down there, let everyone know that this is now working. So if you're watching this video in the future, check the pinned comment out. This issue may be fixed, and it might be absolutely fine. So I'll leave that down there if I get a solution to this issue. But for now, it is a little bit weird, so I really hope they can fix it, but until they can really get this issue fixed, unless you're happy doubling up your CTs and essentially using it as a 3-channel energy monitor, the power factor measurements and resulting sort of real power measurements just aren't very accurate. But other than that, it is a really good device. I really like the sort of ease of setup. The fact I can set this up without any kind of app or cloud account and I can just pull the data straight into Home Assistant is absolutely fantastic. It's just got this one issue that they really need to fix before it's really usable in a sort of live environment. But yeah, there you go. Hope you found this video interesting or potentially useful if you're looking to do sort of whole home energy monitoring. And also stand by for tons more videos where I'm going to be doing even more energy monitoring in various different circuits and various devices. So I'll be doing loads more videos on that. And if you're interested in buying this device, the Refoss EM06P, I'll leave links down in the description and in a pinned comment. But of course, just bear in mind that this is currently a bit of an issue. Don't buy a device based on promises of future firmware updates fixing issues. But if they fix this, I'll definitely leave a note down there so you'll know that this device is actually working and ready to buy. But all I've left to say now is thank you very much for watching.